Okay. It's good? Okay. طيب بسم الله الرحمن الرحيم. So we talked last time about the CISMA CA or carrier sense multiple access with collision avoidance, and we said that because we cannot detect collision in case of wireless, for example, we have to do some stages in order to avoid collision because we cannot detect it. So we try to have some buffers, or we try to have some ways to prevent the collision from happening, because when it happens we cannot detect it and the cost will be expensive. So what we have discussed is that we use the interframe spacing as one of these stages, and then we use what we call exponential contention. So we use what we call a contention window, which is divided into time slots, and for each time slot we use a parameter which is called K to calculate the contention window. And within this contention window, each node will independently generate a random number, and based on that it calculates which time slot that it needs to check to access the channel. And then during these time slots, every time slot I have to continuously check if the channel is idle. And if the channel is busy, then we stop and we reset everything and we start from the sensing stage again. Okay? So if the channel is idle after the contention, if I continuously sense the channel and then I discover that the channel is idle, then and only then I can send the frame. Okay? So when I send the frame here, there's no way for me to detect whether there is a collision during the transmission of that frame, unlike CISMA CD. Okay? So the only way for me to figure out that there was a collision is by timeout. So when the timeout happens, this means that I did not receive the acknowledgement within the timeout. So this indicates to me that there may have been some collision or some packet loss or something, and the result for me is the same. I have to retransmit. So the interframe spacing can also be used to define the priority of a station or a frame. And this is a very important and interesting issue, that the interframe spacing, if it's constant for all nodes, then all nodes will have the same priority more or less. If it's shorter for some nodes, this means that these nodes have higher priority or lower priority. Higher priority or lower priority? So we try to contend, we try to struggle to access the channel. So one will wait for an IFS, which is shorter compared to other nodes. Will that node have higher priority or lower priority? The node will access the channel more likely or less likely? More likely? More likely. Why? Because if I wait for a shorter time, there is a high probability that I will start accessing the channel before anyone else does. Right? So if there are some other nodes with larger duration for the interframe spacing, they will have to wait for a longer time, in which case I will win. Yani I will be the first to access the channel, which means I have higher priority. So by changing the interframe spacing between the nodes, I can provide some priority scheme or some priority mechanism. Okay? Also, if a station finds out that the channel is busy, it does not restart the timer of the contention window. This is also very important. This happens during the contention time. So I waited for interframe spacing and then I access the channel. I find that the channel is idle. Then I don't access the channel right away. What do? I have to calculate the contention time. Based on the value of k, I generate the duration, and then I generate a random number within that duration. Okay? And then I set my timer. The random number, for example, is 10. Then I have to wait for 10 time slots. Each time slot is, the duration of this time slot is the propagation time, the maximum propagation time. So in that case, I have to wait for 10 time slots. Okay? I don't just stay until the timer expires after 10 time slots. No, every time slot I have to continuously check the channel again. So after one propagation time, I check the channel. The channel is still idle. After one propagation time, I keep checking the channel. If at time slot 5, I realize that the channel has become busy. This means what? This means that another node is contending on the channel, and this node decided to access the channel before me. So in that case, what do? I have a timer which is counting, which is ticking, okay, and it will expire after 10 time slots. So what do I do when I figure out that the channel is busy? What I do is that I reset the timer. As we said that when this event happens, we have to go back from the beginning to start continuously sensing the channel until it becomes idle. So in that case, I reset the timer. Okay? So we don't restart the timer, we don't suspend the timer, we reset the timer. Because we have to start from the beginning. This means that I lost the chance to access the channel at this point in time. Therefore, I have to go back and continuously sense the channel. When the channel is idle, then what I do is that I have to wait for interframe spacing. And then, after this interframe spacing, generate a random number. Okay? After I generate a random number, then I keep counting the time slots. And if during this counting, the channel has become busy, then I have to go back from the beginning. So I have to keep doing that until I make sure that I wait for interframe spacing, the channel is idle. I wait for the contention time and the channel is still idle. Then you can access the channel. Okay? Following? So with that said, this is the procedure. And as we can see, the procedure is significantly different compared to Cisma CD. So the first thing we notice is that this branch has changed significantly. So we notice here is that we have acknowledgement instead of detecting the collision, because here we cannot detect collision. So the only way for us to figure out if there was a collision is to wait for a timeout. If the timeout expires, then without receiving an acknowledgement, this means that there was an error, and then I have to retransmit. So in that case, if I continuously sense the channel and the channel is busy, then I keep looping here. If the channel is idle, then I have to wait for interframe spacing. When I wait for interframe spacing, I don't do anything until the interframe spacing is finished. Then the channel has become busy, then I have to go back from the beginning. The channel is still idle, then you have to choose the contention time. So you use the K parameter to calculate your contention time. Let me just magnify this a little bit. Okay? So here, you calculate K, and from K you generate a random number within that range, similar to what we have done before. And then, this random number is R, which means that I have to wait for R time slots. I have to wait for R time slots. Unlike the wait for IFS, here I don't just wait. I start the timer, but every time slot I have to wait. I have to do what? I have to do what? I have to continuously sense the channel again. Why everybody sleeping? So I have to wait, after each time slot, I have to wait, I have to check the channel. So during that time, if the channel has become busy, it's not actually illustrated here. But during that time, if the channel has become busy, then I reset everything and I go back from the beginning. When I go into that branch, this means that I waited for the contention time and the channel is still idle. When the channel is still idle, then I can send. When I send the frame, I cannot detect. So unlike the Sysma CD, when I send the frame, I continuously sense to see if there was a collision, because I can detect it. If it happens, I can detect it. How do I detect it? From the energy level. Right? Because here I cannot sense the energy level. So in that case, I send the frame and then I hope it will go through. How do I know it did not go through? By not receiving the acknowledgement. So I wait for the timeout. If I receive the acknowledgement, then everything is fine, success. If I don't receive the acknowledgement, then I increase K. And as you can see, there is no exponential back off in the case of collision. Because I have to do it anyway here. So in Sysma CD, I used to do the exponential back off. I call it back off. Here I don't do back off. I actually do a contention. Because I have to do it anyway during transmission. In that case, I don't have to do it in case of collision. So in case of collision, I increase K, and then I go back from the beginning to make sure that the channel is idle, and then I repeat. So this is something that you have to watch for. There is no back off in the case of Sysma CA. So that's another significant difference. Any question? So this category of medium access techniques, they support collision. Okay, so they try to access the channel opportunistically, and then if there is a collision, I have to deal with that collision in one of the ways that we have discussed. First, if I have the ability to detect it, then I will detect it and send a jamming signal. If I don't have a way to detect it, then I have to make sure that I receive the acknowledgement. If I don't receive the acknowledgement within the timeout, then I assume that there was a collision or there was an error, and then I try to retransmit. In this category of techniques, what we try to do is that we try to eliminate collision. So starting from this technique, the reservation and polling, we try to eliminate collision completely. Okay? So in the other two categories that we will discuss, there is no collision. So in that case, I have to make sure that when a channel sends any frame, I have to make sure that within the entire network, this is the only node that's sending at this point in time. Okay? So in that case, I can do that in different ways. Okay? The easiest way is that if we go back to our famous example, the meeting scenario. We just need to make sure that whenever someone speaks, he's the only one who's speaking at this point in time. Okay? So what are the different techniques or ways that we can use in order to make sure that one person at a time speaks? Because if there are more than one, if there is more than one person, then there is a collision. So we try to eliminate this completely. So the first category is that we use what we call reservation. Okay? Reservation or pooling. So in the reservation technique, what we do is that, again, if we try to explain this in a meeting scenario, we agree in the meeting that every now and then we say who has something to say, then user or member, let's say member 1, member 5, and member 8. They raise their hands. I have something to say. Okay. Then we say, okay. Member 1, go. Member 5, go. And then member 8, go. After they finish, we go back and say, who has now something to say? Okay. Member 2, member 10, member 15. Then we say, okay, member 2, go. Member 15, go, and so on. Okay? So in that case, we have an agreement to follow that mechanism. So the way it works is that we have what we call many slots. So these many slots match the number of users in the network. So if we have 5 users in the network, we have 5 many slots. Okay? So these many slots are very short time slots. Okay? And it's like someone raises his hand to say, okay, I have something to say. So these many slots are sent as broadcast in the entire network. And then the users will set a flag to say, I have something to say. Okay? So in that case, user 1, user 3, and user 4, they have data. They have something to say. So this means that I'm expecting user 1 to go first, and then user 3, and then user 4. So that the time is this way, by the way, not as the arrow indicates. Okay, so we have many slots. So each node will fill its own many slot if it has data to send. Then, based on the flags in the many slots, only the stations that set this flag are able to send. So in that case, here, I know that node 1 has data to send. So in that case, because this many slots will be broadcast to the entire network. So all other nodes will wait for station 1 to finish. And then after that, station 3, and then after that, station 4. Okay? So these many slots may have the length of the data that station 1 needs to send. So station 1 will fill this flag to 1 and will also set in the many slot that I have a data with length X that I need to send. Which means that other stations will be idle during that entire time. So the other stations will calculate based on the bandwidth, based on the length. They know that the transmission time can be calculated easily, and then during that time they are not allowed to send anything. So they calculate transmission time, they calculate propagation time, and then during this entire time, they cannot do anything. And then after that, station 3 goes, and then after that, station 4 goes. So this way, I can make sure that there is no collision. And then after that, I repeat this process. Okay. So this way, I can eliminate the collision. What we can notice here is that the reservation mechanism can be done without having a coordinator. Yani it can be supported without having a centralized node to control these many slots or to control who will send when. And it can be done using the centralized node. So here we did not highlight the existence of a centralized node or a coordinator, because it can be done either way, with or without a coordinator. If it's done without a coordinator, then we have to periodically send these many slots. Any node can send these many slots, broadcast to all nodes, and then based on which node will have data, they will set the flag, and then the transmission will happen. The problem, if you don't have a coordinator, is that if the load on the network is high, usually you don't have any fairness. Which means that here, if all the nodes have data all the time, or if one node has a high probability that it has data all the time, but other nodes, they periodically have data and sometimes they don't have data. So in that case, the node that always has data will access the channel every time. So at the end, you may not have fairness between the nodes, because there is one node that accesses the channel much more often than others. So this is the main issue in that mechanism. Okay? So this is the reservation mechanism. The other mechanism is what we call pooling. By pooling is that here we definitely have a centralized node. We have to have a centralized node, which represents in the meeting example as a coordinator, okay, who controls who accesses the channel or who receives the data. So in the polling mechanism, we have a primary node. So this is similar to, this is different from Wi-Fi, but I mean, it's the same architecture. We have a primary node, which in the case of Wi-Fi is the access point. In that case, everything has to go through the primary node. Everything has to go through the primary node. So here we have what we call a star topology. So in that case, we have a primary node, and we have nodes around it. Okay? Anything has to go through the primary node, which means that if this node wants to send to this node, it cannot send directly. So it has to send first the frame to the primary node, and then the primary node will send in another time slot, will send it to the other node. So everything has to go through the primary node, which you can consider as a disadvantage. However, by flowing everything through the primary node, you have a well-organized way to make sure that whoever is accessing the channel we will not have two nodes accessing the channel at the same time. So what will happen is that the primary node will either have an uplink or downlink scenario. So whether you have data going from one of the nodes to the primary node, or you have downlink scenario where you have the data flowing from the primary node to one of the nodes. Okay? So this concept is what we use in Wi-Fi, what we use in cellular networks as well, using the base station.
The channel between the nodes and the primary node is not shared?
The channel is shared.
So we will have the same problem between the node and the primary node. If multiple nodes want to send at the same time?
Collision will happen. Yes, definitely. So that's why we need to, that's the main reason that we need to have a primary node to organize who can send and who can receive. Okay? So the way we do that is that the primary node will have, as we said, a downlink. This is the downlink scenario. So this is what we call downlink. And this is what we call a uplink. So in the downlink scenario, the primary node, remember we're using a polling. In the polling, the coordinator or the primary node or the central node will always poll. Okay? Will always initiate the transmission, whether it's uplink or downlink. So in that case, we use two control signals. In the downlink case, we use a control signal called select. So I'm selecting a node that will receive the data from me. Okay? In the uplink case, we use a signal called pull. Pull means that I ask you, do you have data to send? If you send me an ACK, then you don't have data. Okay? Otherwise, if you have a data, you can send it. At this point, you can send it right away. Okay? So in the case of the downlink, I have to inform a specific node in the entire network that I have data for you. Are you able to receive it? He replies back with an acknowledgement, which means that, okay, I can receive the data from you. Then I send the data and wait for acknowledgement. Okay? So in that case, the primary node will send the data and wait for acknowledgement. The question is, why do I have to wait for acknowledgement if we say that the collision should never happen? Collision is not the only source for error, right? Collision is one source of any error. But we also have a error due to the channel itself. The channel may have an error. So I'm the only one who's sending, but we have noise on the channel. So there is a probability of error, right? So in that case, I have to wait for acknowledgement. So in polling, the primary node will always pull or select a node for receiving or sending any data. So in the case of downlink, I use the select signal. In the case of uplink, I use the pull signal. Okay? Easy? So having a centralized node or a primary node always has advantage and disadvantage. Okay? This is the case for Wi-Fi, this is the case of cellular network with a base station. It's one of the cleanest and easiest way to organize or to make sure that you will not have any collision. Right? Because you have one controller. You have one node that controls everything. So when I select a specific node, how do I select a node in the network? When I send the select signal, I put the MAC address of that node. Because the select signal is broadcast. But in the select signal, I have the MAC address of the node that I'm selecting. So all other nodes will figure out that they are not selected. They will stay silent. Okay? So I select a particular node. In that case, I make sure that no one else will send at the same time. Okay? So this is a clean and easy way to make sure that there is no collision. The problem comes that if there is the primary node always represents a bottleneck, right? So if the primary node has any problem, the whole network is down. Versus in the case of SYSMA, in the case of all the techniques that we have discussed before, there is no primary node, there is no centralized node. So in that case, if a node has an error, this node has a problem, but the entire network is still up and running. So when you have a centralized node, you always have advantage and disadvantage. It's easy to eliminate collision by organizing the access to the channel, but if in case that this primary node has a problem, the entire network is down. Because we cannot have any ad hoc communication, a node communicating to a node without going through the primary node. The other problem is that, and again, this happens in the case of Wi-Fi or cellular network, that even I'm trying to communicate with someone who's right next to me, I have to go through the base station. So if two people are next to each other and they are both very far away from the base station, in order for me to send to him, I have to send to the base station or to the access point or to the primary node, and then the primary node has to send to that person. Even though this person is right next to me, so if I can send to him, I will spend no time. First of all, I have to spend very low power because he's right next to me. So I can send right away in one time slot. The data has reached the person and that's it. Right? But the problem here is that we cannot guarantee that when we do that, someone else might be sending at the same time and the collision will happen. So in order to eliminate the collision, we have to always go through the primary. So even simple transmission like this has to go through 2 time slots instead of just 1 time slot. So these are issues. Even though having a centralized or a primary node seems to be one of the cleanest and easiest way, because when you have one controller, you can control things better. Even from the perspective of security, from the perspective of controlling the fairness of the network. It's very easy. Why? Because the sequence of selection or pulling is controlled by one node. Then this node can calculate this sequence in a way that optimizes the performance. And the performance here is based on the fact that when you send data to the nodes, there is a very low probability of error. And also at the same time, you have to make sure that you have some fairness between the users. If we take the scenario that many users, we all have cell phones, right? And we're all most probably connected to one base station out there. But this doesn't mean that all of us have the same channel to the base station. Someone might have a better channel compared to the others, right? So if that one is accessing the channel to the base station, he has or she has higher probability of getting the data successfully to the base station. Whereas if I try to send, maybe I have lower priority, or sorry, lower probability to get the data successfully to the base station. If the base station is intelligent enough, it should try to let the user with the better channel to access that channel and send, because he or she has lower priority to access the channel. However, if that person has good channel all the time, he will be the only one who accesses the channel. So in that case, other users will not have any opportunity to access the channel. So in that case, we have a compromise. You have good channel, I will give you higher probability to access the channel, but I have to also be fair to others. So this is what we call scheduling. So the polling mechanism, whether select or the pull signal, it has to follow certain schedule. And this schedule has to take into consideration those two factors. The throughput, based on increasing the probability of successful transmission, and at the same time fairness. It has to have some compromise between the two. And scheduling is one of the very critical topics in any type of wireless communication, especially wireless communication, whether it's Wi-Fi, cellular, and everything. Okay. Because we always have, in case of wireless, the spectrum and the channel has lots of sources for error, right? So what we try to do is that we have multiple users, we have tons of users. If we can have a better scheduler, we make sure that when a user sends, or when we send to that user, the channel is very good, that we can get the data across. And at the same time, this user has a fair share of the channel compared to other users. So these are two, in many cases, conflicting factors. Performance, in terms of throughput, and fairness. They have always conflicting objective. So in that case, we need to have a trade-off. We need to have a compromise between the two. Okay? So polling is one of the mechanisms that we can utilize scheduling to give chances to users in different times. Which is what we called before different priorities to users. So in the case of SISMA CA, remember we said that by changing the IFS, we can give different priority to users. Here, by controlling the sequence of the selection or the pull, right, from the primary node, we can give different priorities to different users. So we have to use different scheduling mechanism based on the channel access mechanism that we have. So in the case of SISMA CA, we have some means through changing the contention time or changing the IFS to give different priority to different users. Here, since we have a primary node, we can control the sequence of the selection or the sequence of the pulling. Okay? Any question here? So we said lots of details on this slide, even though the graph is a bit simple, but so that's the second category. The third category is what we call channelization. In the second category, we said that we have to control the reservation of the channel, or we have to pull the different users to access the channel in order to eliminate the collision. Here, our means to eliminate the collision is to divide the resources of the channel, okay, prior to the communication. And the way that we divide the resources of the channel is either by changing the frequency, changing the time, or changing what we call the code. So we have what we call frequency division multiple access, time division multiple access, or code division multiple access. So we have 3 techniques in that category. We divide our channel spectrum into frequency ranges. So each node, okay, will have a transceiver or a transmitter and receiver which is capable to transmit or to receive data within a specific frequency range. However, this node may in fact use one frequency range at a specific time, and it may actually decide to move to another frequency range at different time. Okay? So even though I have a big frequency range for all the users, but I have to divide this frequency range into smaller, what we call sub-channels. So I have one channel, assume that we're talking about wireless. We have, let's say, 100 megahertz, 100 megahertz bandwidth. This is the bandwidth for the entire network. And then I have 10 nodes. Then I say, okay, I will allow node 1 to send from from 0 frequency to 10 megahertz. So node 1 will have 10 megahertz bandwidth from 0 to 10. Node 2 will have 10 megahertz, but from 11 to 20, and so on. Okay? So in that case, if different nodes are sending on different frequency, even though they are sending at the same time, but the collision will not happen. Why? What can we use in order to allow 2 people to send at the same time, even though I can extract one from the other? What can we do in order to 2 people are sending signals at the same time, okay, on different frequencies? Can I extract one signal from the other, and how? What do we do in order to extract one signal from the other? Interaction.
We should have space in the signal so they don't interfere.
Space as a frequency space.
Yeah.
The frequency space has to be there. But أيوة مين الفلتر? Okay. Yes, you need to have a filter because they are sending at the same time on different frequencies. So the only way for us to extract one signal from the other is by having a bandpass filter. Bandpass filter is the way to extract one signal from the other. Okay. The space, we call it guard band. So in that case, we do have guard bands, and here we're talking about frequency guard bands. So we do have guard bands here. So between the channels, we do have guard bands. But that's because the filters are never ideal. So the filters, they are not like this. They always have something like this. Okay, so they are bell-shaped. So in that case, we need to have guard bands in order to make sure that when we extract one signal from the other, there is no interference, there is no overlap between the two nodes, the subchannels of the two nodes. Okay? So here we have to use filters. So each node has to have a filtering, bandpass filtering mechanism in order to extract its own signal from the transmission of the composite signals. Okay? So we'll discuss the TDMA next time.